Oh, yes. Good afternoon. Let me close my music. Sorry for that.
Not an issue, yeah.
How are you today?
Dr. Bhatt is here. Hello, Bhaji.
Hi, good afternoon. Good afternoon.
Glad to have you today. We missed you in the last.
Yeah. I really missed it actually. Yeah. Some of the commitment actually.
Okay.
We are ready to start.
We're still waiting for people, I don't think.
Yeah, I think let's
we are the only three here right now.
Oh, I see. Okay. It's not at 3, so we can wait for it.
Right.
Yeah.
Are we at about 50% of the planned series of talks, or?
Well, I think it's more than 50% now, unless we want to deliver some more lectures on other topics. So
I see. Okay.
Let's see how it goes.
Yeah.
How is Professor Dinesh interested in more topics?
So, Bhaji, we were talking about analysis and design of joints. And
yeah,
also
that's
analysis and design
yes.
for
I'll cover that. Sure.
Yeah. This last talk, is it the previous talk?
No, it's a separate course other than the certification course that we are having right now. But essentially into certification, but focusing more on the joints and damage tolerance. So these were the two additional courses that we were considering, which I think a lot of people be doing research in those fields will be benefited.
Yes. Joints, when you talk about, not necessarily composites.
Well, they're bolted joints, bolted composite joints.
Bolted composite joints. I see. Yeah. Okay.
Bolted because joints are very important part of the design.
Yes. Sure. Very nice. Sure. That is after the series of the certification.
Yes,
we are planning.
I think I'll finish up certification today. Possibly, and next week I would take up a bolted joint.
Wonderful.
Okay. Great. Yeah. Sure.
Hello, Jeben.
Hello, sir.
We're a small group right now, so we can talk to each other.
Yeah, I was initially a bit confused if this was a private meeting.
Where are you, Dr. Garg, just now? Where are you speaking from?
Melbourne.
I see. Okay. Melbourne, from your home, is it?
Yes, I'm at home. I'm retired these days for last 1 year. So, and we are under lockdown. We can't just go out at all in Melbourne.
Oh, Melbourne, yes. Melbourne, I heard for total lockdown again.
Yeah, it's a tough lockdown over here. And suddenly the COVID cases are just increasing in spite of lockdown. Today, 38 cases. Yesterday, there were 930. So they've been just jumping.
How about the vaccination drives and all that?
Oh, vaccination drive is going very strong actually now in Victoria. They have covered 80% of the people or eligible people for the single dose and double dose about 50%. So, and they expect to hit 80% in about, I think, 8 to 10 weeks.
Okay. So are they going in batches, giving priority to senior people first and things like that?
Well, now everybody is, can have vaccine.
Okay.
Initially, they started with senior, but now from, I think, is it 12 to
18.
18 and all higher. Everybody is entitled for that.
Okay.
So they've been going very strong now.
You have had both your vaccinations done?
Yes, I have taken vaccinations. We finished on 1st of August. Both the doses were completed. So,
which one was that? Pfizer?
AstraZeneca at the time. Now, of course, mainly people are taking Pfizer and Moderna.
Okay.
there was a scarcity of Pfizer at that time, but
Okay. Okay.
I believe both are, all are similar. There's not much difference
Yeah.
in
Simply the brands.
immunity level.
Yeah. So how much gap do you have to give between two doses?
Well, now, actually now Pfizer earlier it was 6 weeks. Now they've started 3 weeks gap only.
I see. Okay.
And AstraZeneca used to be 12 weeks, which they cut down to 6 to 8, I think.
Okay.
So it has been moving pretty well, but somehow it's really scary thought of
Yeah, I know.
case numbers going up again in spite of vaccinations. Other countries also same thing, USA, UK, in spite of vaccinations happening, quite a large number of people have taken vaccination and the cases have been going up. Same thing in Canada. So it's a scary thought again. This
Yes, yes.
COVID is not stopping.
Okay. Just now it's quite under control in India at least. So just keeping our fingers crossed that it doesn't again.
That's good actually. India had a bad time in May when a lot of people were dying due to the scarcity of oxygen, hospital beds. It was pretty scary.
You are talking about 35, 40 cases per day. We used to have kind of nearly 4 lakhs in a day.
Yes, I understand.
Adding,
That level in Australia, it will be very frightening. Australia population is very small. One is 1:50 ratio compared to India. We are only 25 million.
Yeah. Did you feel any after effects after the vaccination?
No.
Just nothing.
Slight, I think. One day only, little feverish I felt, but not anything significant.
So how about the supply of regular food items and things like that for you people? Online you order and something like that?
Oh no, I never buy online. We just go to the grocery shop. The grocery shops are open. Other shops are not open, but grocery shops are open here. So we just drive. It's only about 1.5 kilometers, the grocery store, and we just drive.
So all essential stuff easily available.
Yes, everything is available mostly. So it's not that bad over here. Okay, I think it's about 7:36.
Yes, we can probably go ahead.
We can start. Okay. Good afternoon, everybody. And let me start with my question answers slide. Share tray. Questions. Okay. Now I'll just start with the question answers and a few queries which were there last time. Also, there was an unanswered question from the previous sessions almost 2 weeks back when somebody asked whether the cabin noise for the composite structures would be lower or composites structure will attenuate or reduce the noise level compared to aluminum. In fact, the other way around. The sources of noise in the cabin, suppose we are considering, forget about takeoff and landing, but cruise is main concern over there because most of the time of passenger we spend during cruise. So during cruise at high speed, the main noise inside the cabin is due to the turbulence boundary layer on the wing and fuselage surface, which causes the noise. It is found, usually the typical exterior noise level is around 135 decibels, which is overall sound pressure level with a peak to peak 1/3 octave around SPL of 125 dB. Okay. In the interior cabin, the requirement is at least the noise should be below 85 decibels. Normally it's around 75 to 80 decibels, which is comfortable. And now the issue with the composites is composite skins. Composites are stronger than aluminum in terms of the specific strength and specific stiffness. And it has been found the skin surface density, because skin then becomes thinner. So we are calling a skin surface density is almost 70% of aluminum skin density, surface density. Due to that, thinning of the skin of the composite on the contrary to aluminum, the noise absorption capability of composite skin is lower compared to aluminum skin. So in order to achieve the lower acoustic noise inside the cabin, that means you have to provide extra insulation to the composite fuselage compared to aluminum. So there's a weight penalty. However, that weight penalty is not significant in the sense already the weight reduction is significant due to the composite skin, composite fuselage. So even though the acoustic lining increases in weight, the total gain in weight is still there. So what I found from some work from Lockheed, this is the work done.
Dr. Garg,
yes.
1 second. Can you go to the previous slide? Yeah. Can you just explain a bit about what do we mean by surface density? 70%.
Oh, surface density is nothing but basically the mass per unit area.
So yeah, composites will be about 0.7 times aluminum. Okay.
So what happens due to this one? So the skin is getting thinner.
Okay.
Now this is what I'm quoting is really the Lockheed work which they had done about 30 years back.
Is it about the thickness of the skin or is it about the area of the surface? Well,
surface area means naturally if thickness is coming down,
okay,
over a unit area, the weight also will be down.
Yes.
So naturally that is what it calls surface density is correct.
So this noise is not dependent upon only the area of the surface. It is more about the surface density. Is that so?
Oh, well, it is basically surface density, because what happens, there's a frequency function. Frequency is a function of root K by M essentially.
Yes.
So
yes.
That way it is multiple effect, but this is I've quoted in summary from Lockheed work basically, which they had done almost 30 years back when they were investigating the composite versus aluminum fuselage. So I went into that report. And basically, I can send you the references. There are 2 references which mention this exactly the issue which I'm talking about. I have taken only the abstract from that. So it's a real thing which has been done.
Right.
And what they found, they had to provide more lining, acoustic lining for a composite fuselage than aluminum. In fact, I was surprised because I also thought composite skin, because it's a viscoelastic material, it would have more attenuation due to damping characteristic. Damping is higher.
Yes.
But it's not so.
Not so. Okay. Okay. Thanks. Right.
So I think somebody has asked a question, so I thought I'll better qualify it. And I delayed it because I just wanted to look from the real references if some work was done already. And this is what I gathered. I can send the reference of the Lockheed report from where I picked up.
Thank you, sir. It will be good if you could send the reference also. This was exactly what I asked.
Yes, I'll send you the reference.
Thank you, sir.
Okay. But it's interesting to know, basically, even I was not familiar about it. The next thing was someone had asked a question when, in fact, I would be covering this joint issue when I'm talking about the bolted joints, but I thought there was somebody had asked a question regarding, well, when I said the design of a bolted joints become critical, especially fatigue we have found is more critical, and we have to ensure the fatigue life. And after a lot of experience of the joint designs over here, I would always insist any joint in composite with bolted joint basically should be designed with a fatigue criteria. That's what we found. Now, the question was regarding this one when I was showing a slide on the fatigue issue of the joint, that whether it's due to the clamp up, and I did explain, yes, the clamp up, but however, the clamp up is taken into account. So when we are doing the static joint analysis, we consider the reduced clamp up, which is validated by the test data. We determine the bearing strength using the test with the reduced clamp up, usually around 50%, or if you decide to go a bit lower, probably lower top. And then based on that, bearing strength level is determined, and that's used in static. How when the fatigue is being done, fatigue analysis, fatigue joints are tested, and there's no analysis criteria available. In fact, for a fatigue life prediction for the bolted joint is difficult. You may have to determine some like empirical relationships in order to determine the fatigue life. And that is based on the test data with various parameters. So coming back to the clamp up, the procedure to determine the fatigue life when we are doing the testing, we make the joint as production procedure, and that is coupon with 100% clamp up, because that's what in production the aircraft will be delivered with 100% clamp up. Even though we design with a lower clamp up, but production has to be 100% clamp up, fully tight bolts. So in order to test the joint, what we do, we will relax it for almost like maybe a couple of 100 hours before you start loading in fatigue. So if there is some relaxation, it would normally occur within that time mostly. And then of course it's a small reduction. And you start loading in fatigue, of course, fatigue will cause another probably some relaxation, there are shame, sealant, and all those effects you have to generate through the test data. So essentially it's the test which will take care of all the parameters, shame, sealant, relaxation, and then you will determine the fatigue life. So essentially it's a function of several parameters in the joint, which I'll be talking while talking about the bolted joint. So I won't discuss much detail about it. I thought I'll just give a brief background about it.
Yeah, and, Dr. Garg.
Yes.
I also understand whether it is covered here. I understand that also the type of bolt joint in terms of whether it is a push fit or interference fit kind of thing has a major effect on the behavior of the joint.
Yes, it does. This is what I'll talk in my bolted joint lecture. Usually in composites, we don't use interference fit.
Right.
They are clean fit.
Clean fit. Okay.
We call them class 1 joints, holes, which normally class 1 holes, according to definition, is maximum clearance is about 0 to 3 thou, and 1 thou. Let me just think of, I'm used to that American convention. I think one. Come on.
Anyway,
this is 3,000th of an inch.
Okay. So
I'll be talking about that in my.
In
fact, I've covered that interference fit, the effect of interference fit, also in my bolted joint lecture notes. So most of the parameters are covered to make it clear. Okay, the next one, I think there was some question about the bonding surface preparation. Of course, there's nothing over here much. Usually, I've just shown say parent laminate and the repair when you are laying up the ply with the adhesive. The process for the composites, surface preparation is not as what happens with the metallic adhesive bonds. In composite, generally, the moisture is removed when they are repairing because you have to dry up the parent laminate or the part before you can repair, because moisture, if there's a moisture in the laminate, it degrades the joint significantly, adhesive value. So drying process and then cleaning the surface by sanding. Now sandpaper will be about 150 or 250 grades. That convention, I don't remember now, but an appropriate sandpaper will be used in order to sand it. And then just remove the dust and lay the adhesive. So all those processes, I can't mention all the processes over here, but there are processes which are given to the airline, how they will repair when there's a damage. So I'm not going to the details of this one. I thought I'll just clarify. So this is all, unless somebody has questions from the previous lecture before we proceed. No, let me just go to the certification. I think last week we had finished up to these various manufacturing defects. Did I cover this slide last time? Anybody? Oh, sorry, you can't see. I have to just share this tray. Okay. Can you see this slide now?
Yes, yes. Manufacturing defects.
So did I cover this last time? I don't remember.
Around 190 slide number you have covered, sir.
Oh, so I had covered this, is it? Yeah, I think so. Because I said, okay, I'll cover this. Start from subcomponent test.
Yes, sir. Yes, sir.
Okay, now after finishing the coupons, the labels, coupons, element test, now we consider subcomponent. Subcomponent, nothing but basically a detail of a structure involving a few more details compared to what you have with a coupon or elements. So essentially, it's a bigger item or bigger part of a structure, subcomponent. So effect of structural complexity and scale up upon basic reliables, data and data analysis methods, verification of analysis methods, secondary effects and redistribution effects of loadings, effect of damages, static and fatigue, effect of static and fatigue on complex joints. Okay, so first thing which in this I'm trying to discuss is the lightning strike effect, which is an important part of the certification because there's a requirement. Okay, F for 14 CFR 25581 for lightning strike, it states that the airplane must be protected against catastrophic effects from lightning. For metallic components, compliance with paragraph A of this section may be shown by bonding the components properly to the airframe or designing the components so that a strike will not endanger the airplane. For non-metallic components, compliance with paragraph A of this section may be shown by designing the components to minimize the effect of a strike or incorporating acceptable means of diverting the resulting electrical current so as not to endanger the airplane. The difference between metallic and composites is composites are basically non-conductor. Metal, aluminum is a conductor, and that's what makes it a different scenario for the lightning strike for the composites, which have to be protected against the lightning strike causing any damage. Okay, now just to explain some zones. So this is an aircraft I've just picked up from the internet, this picture as a typical picture. So zone A, we define the lightning strike in 3 zones of the aircraft. So zone A, 1A and 1B, which are shown by this red, it's 1A, and this 1B. So essentially, the highest current occurs in this 1A zone. Initial attachment point, low probability of flash hanging on, and typical current is 200,000 ampere, which is pretty high, causing the damage, which normally occurs almost like a leading edges of this you can see on the surface. 1B, initial attachment point and high probability of flash hanging on. So this is the difference between these two, and current levels are high. Then zone 2, which has much lower, of course, current levels. So the damage created due to this, if lightning strike occurs in these zones, is much less. So there's swept stroke zone, low probability of flash hanging on, typical currents 500 ampere. Zone B, swept stroke zone, high probability of flash hanging on. So essentially in zone 2B. Then zone 3, which is very small level of current, in fact, conducted currents, no actual attachment to lightning strike. In zone 3, which is essentially these surfaces. So very little damage created if the lightning strike, because they are not very high current, low probability of any direct attachment to lightning strike pressure. So depending upon your components, one has to look into the zone and try to justify based on the current levels by testing and analysis. So say the industry like Airbus and Boeing would have generated a lot of data for various materials for various zones. The effect of lightning strikes, metallic structure, normally pitting, burn marks, or small circular holes or group of holes in one location, or divided around large area, burned or discolored skins, melt through structure, burn indication around fasteners, missing structure at airplane extremities. Normally metallic structures don't suffer as much damage as the composites, the small damages. In composites, burnt paint, damaged fiber, composite layer removal, burn indications around fasteners. As you can see here, indications, composites require lightning protection because there could be large damage, and I'll show you in the next slide after this. So lightning strike compliance is done by lightning protection to joints and anchorage in critical areas, assess lightning strike damage, coupons and subcomponent test, and damage tolerance demonstration of lightning strike. One of the key area of the lightning strike protection is in the fuel tanks, because fuel is located all around the wing, and there's a strict requirement for lightning protection criteria so that the fuel doesn't burn, because there are fasteners which can conduct and then create a flash inside the fuel. So lightning strike test, in fact, during 787 program, because this is a new type of a structure at the time, and we had to perform the test for the lightning strike, what kind of damage it would create. So this test was done in Seattle, because in Melbourne we don't have the facility for lightning strike test. some panels were created over here, and then in Seattle they impacted with different voltage and current levels, and this is just one strike point showing a large damage. You can see scale, and I don't remember what was the current here and the voltage, as this is not in the paper presented. Whatever information is in the paper, that is only what I can state here. So now you can see from this scale, virtually almost 3 inches damage. It's a severe damage. And so what happens when you are trying to justify now using this damage? Okay, such a damage will be visible. If it's a very large damage, it becomes a visible damage, and the criteria of visible damage is followed for such damages. So suppose we are treating like a 4-inch hole or 100 millimeter hole or 150 millimeter, we would try to determine the residual strength and consider what is the residual strength of that, whether it's a limit load carrying capability or less than limit, and try to design the structure for tolerating this type of damage as visible damage criteria. So this is all in the lightning strike. I won't go into the details of this. The lightning strike protections, depending upon the zones, could be done by like a bronze mesh or aluminum mesh or some other means to protect the structure from lightning. And in some regions like these flaps, because here these flaps lie in zone 3, which is not very critical area, so no lightning protections were required in the flaps. However, we had to just determine, in case if something happens, the damage resulting from lightning strike, which was, and also these fasteners. Normally, lightning hits and damages the fastener in service. There have been quite a few cases when lightning has affected these fasteners and created damage in the trailing edges of these flaps in service. So when the damage occurs, of course, the airlines would contact Boeing, or if the damage is within limits prescribed by the repair manual, they will repair it, or else they'll go to Boeing and Boeing will provide the solution for the damage repairs. Okay, next is the body strike damage. This is a very important part of this damage tolerance. And every year some body strike damages occur for some airplanes around the world. I'll just put up a picture and just superpose some birds over here. It's not a real thing. Criteria for a body strike requirement is damage tolerance evaluation. The airplane must be capable of successfully completing a flight during which likely structural damage occurs as a result of impact with a 4-pound bird. When velocity of the airplane relative to the bird along the airplane's flight path is equal to VC at sea level or 0.85 VC at 8,000 feet, whichever is more critical. So this has to be demonstrated for the structure, and we had to demonstrate. I'll just show you some slides over here. And then another criteria for body strike damage 631 is the empennage for vertical, that is empennage structure, horizontal tail and fin, must be designed to assure the capability of continued safe flight and landing of the airplane after impact with 8-pound bird. So this is double of that 4-pound bird requirement, which is a severe damage requirement for that type of structure like a empennage structure. So this has to be again demonstrated for empennage structures. For our structures, the requirement was 4-pound bird. Although, let me just say, depending upon, suppose industry wants to go ahead with a larger bird to show the compliance, which is not required by FAA, but to show themselves for a bit more fence safety, then probably industry will choose to go higher. Okay, now, what is the compliance philosophy body strike damage? It has to be validated by test. However, tests are expensive, so a lot of work has been done by the industry and by universities, and some softwares have been developed like PAM Crash, LS-DYNA, MSc Dytran, which simulate the bird strike damages to determine the effect on the structure due to the bird strike, how much damage is created, and what is the remaining strength or residual strength of the structure. You can just search in the literature and you can find these softwares and a lot of work done by many of the universities and the industry to understand various packages. In fact, recently, the Boeing has been doing work for the NASA contract because there's an open literature at NASA website. They have been developing some sophisticated modeling using LS-DYNA to determine the bird strike impact damage. Because as he said, the tests are expensive. So if one can develop the analysis capability, that will significantly reduce the cost to the industry. And the models have to be very reliable. So I can send some references if somebody is interested in that, like some PhD students. The impact damage simulation. Results. Interface loads, structural damage, stresses and strains, and test the structures simulated or real bird strike. Result, interface loads, structural damage, stresses and strains, because that is validation, basically. You make the model, analyze it, and verify by test. Once you have done that, of course, then analysis method verification, then you can apply this method to other zones because you can't test every region of the structure to understand the impact damage due to the bird. See the next slide. So previous slide, develop equivalent cannonball damage. Now, what cannonball damage is, I'll show next slide. Simulate damage to the structure, residual strength, and margin calculations. Okay. Now this work was done by Boeing and Corporate Research Center in Melbourne long back for 787 program. However, I could present this because it's an open literature, it's a published material. It was done by my colleague Steve Georgiades. He's also retired now from Boeing. So at that time when the PAM crash was used, PAM crash has been used significantly by Europeans. And so this was a software which was used in order to simulate the bird strike damage. So a box, like a 70-inch box with multiple ribs, and the spar was fabricated and modeled also, as you can see over here. And then the test was done in Seattle for the 4-pound bird strike, which was simulated bird, gel pack. And as you can see here, when the bird was struck, that's a simulated bird. The real damage to this box over here, this is the damage denotes, and PAM crash simulated damage, you can see. So that was fairly a good simulation by PAM crash of this damage. Lower skin, this is the damage, and simulated damage. So pretty good correlation they could generate between the test and the software, which provides the confidence in the analysis. And then also, so that was only this box. This is just a simple box. This one is a real outboard flap, pre-production for 787. So this is, you see 787 outboard flap, the real structure. It was impacted with a bird. And the structure with 4-pound bird saw no damage. And this was then validated by the modeling also, no damage to the structure. And say bird strike damage test and simulations. So 787, same outboard flap which I showed in the previous slide. And what happens? Bottom row indicates the damage predicted by this is PAM crash, and this is the real damage. No damage to a structure noted either by simulation or test. This just mark a small damage, but it's not really puncture or any damage to the structure created. So that provided again the confidence in the analysis with the test data. Now I was talking about cannonball approach. So what is there now? What happens here? Say when you are testing can be done only impacting the bird at some angle at one place only. But that doesn't mean that this will cover whole of the structure, because bird can impact here, bird can go through this one in a different angle. So what happens there? You can't test for each angle in each flap, because there's outboard flap, inboard flap, aileron. They could all be impacted by the bird. But testing was done only with the outboard flap. And I'll show in the next slide when I'm showing a component, the same flap, another production flap was tested with a bird, the real bird. This was simulated bird, gel pack, but real bird, and I'll show you later on. Now, so what happens, then you have to, once you have developed your correlation between test and analysis, and you are satisfied with a particular software modeling, then what you will do, you will try to analyze the structure used, we call cannonball approach. What it means, cannonball, suppose you hit cannonball along this trajectory, then the damage will be created. Say, if the ball goes inside, it will go with this path, or if it deflects, then it will create damage over here. So damage is structure. So depending upon these angles of the impact and the trajectory of this cannonball, it will create the damage. So what you will do in practice, depending upon the probabilities of the angle at which the bird can hit the structure at various incidences of the angle of attacks and this bird strike path, simulation will be done. Okay, how much structure could damage? Suppose the bird hits with a greater impact, it just takes away all this material out. Okay. So this is what the cannonball approach is, that we would simulate in the known path for different parts of the bird and remove the structure or simulate the damage created by like a cannonball. And then analyze it. So all this structure, then remaining structure will be analyzed by finite element methods. And then you determine the residual strength to satisfy the damage tolerance requirement, which requires the 70% of the limit load plus 40% of the gust, all those criteria, 25571E, which I have presented in my previous slides in these notes that they are there. Another part of the cannonball, so various damages, basically, you know, when the, say, bird just goes away and slips, creates the damage at other places. All these scenarios are investigated and analyzed in order to show the compliance for bird strike damage to the structure. So that means it requires a lot of analysis. It takes significant amount of efforts, because what happens for each structure, you have to model the damage at various places. Say, considering the flap, so we'll model at various places the damages using the finite element method, because by hand analysis or empirical methods you can't determine. So finite element methods will be used, which will remove the structure and then determine the stresses, strain near the damage, and using some failure criteria like a point stress criteria, which I'll be discussing during my damage tolerance philosophy, to determine the margins or some other criteria. So that's the residual strength approach for a damage tolerance, taking away the structure and showing the residual strength of the remaining structure to meet the required certification requirements. Okay, this is what I was talking about, the real test in Seattle, where 4-pound live bird. Now one would ask, what is this live bird test? What they do, they will pick up a live bird, put it in a barrel, and then hit it. So you can see blood stains because it was a live bird hitting the structure, and you can see only the blood, but no damage to the structure. So this had to be done to satisfy the compliance requirement for 77 empty structures. Now, so only one, this outward flap was tested, and based on this similarity of the substructure and the structure, other like ailerons and inboard flaps were also certified. In addition, the cannonball approach was followed to demonstrate the compliance of the structures. Any questions so far from the audience? It's very quiet.
Dr. Garg,
Yes.
the bird strike effect on a composite structure, by a thumb rule or so, Is it most severe when it hits normal to the surface or at an angle? The same mass, same velocity.
Well, usually what happens, the impact energy will be lower if it is at an angle compared to the normal.
So the reaction from the structure?
Yeah, reaction to the structure would be there. So no, I can't quantify that, because that is again when the bird hits, it creates an impact, and then one has to consider whether it will fail any hinges or the fittings. So that has to be evaluated due to the impact energy calculations and see what is the reaction change. So that has to be assessed. I won't be able to give really the magnitude or how much is the effect. But it's an important consideration that the fitting should remain intact due to the large energy created by the bird strike. Any other questions? Okay. The next part is the phonic fatigue. The sonic fatigue requirements, sonic fatigue strength. It must be shown by analysis supported by test evidence or by the service history of airplanes of similar structural design at sonic excitation environment that sonic fatigue cracks are not probable any part of the flight subject to sonic excitation, or catastrophic failure caused by sonic cracks is not probable, assuming that the loads prescribed in paragraph B of this section are applied to the areas affected. Okay, now, so this is the criteria. Essentially, you have to demonstrate that the high cycle fatigue, basically it's a high cycle fatigue vibrations, do not cause the damage to the structure. Now, I've just shown a typical picture over here, and this is 787 aircraft, of course. And as you can see in the maximum joy, the noise or acoustic fatigue occurs during the takeoff and landing, mainly takeoff, essentially, in the region which are lying in the vicinity of the jet exhaust. And as you can see, this is the engine, and this is the flaperon. 787 flaperon actually lies over here. So in this region, these are fairly close to this exhaust, and they become critical for the sonic fatigue. We had to investigate sonic fatigue compliance using the test data. I'll show you. So essentially, it's a random noise, low amplitude, high cycle, which could run into several millions over the lifetime of the aircraft. Okay, now, cause and effect of sonic fatigue. The aircraft parts in the vicinity of jet engine, there's a noise vibration, high frequency random pressure fluctuations of the acoustic type created by turbulent mixing in high speed jet, efflux or turbulent boundary layer, acoustic loads created by oscillating shock waves, shock turbulence interaction in jet stream may radiate high intensity. So there's a lot of, in fact, work which has been done. You find a lot of publications about sonic fatigue. I won't be able to go into the details of each of these criteria, how they are created. So in summary, they create some kind of a pressures, because it's a pressure which is causing the noise, fluctuating pressures with time. So high frequency, low amplitude pressure cycles that is converted to the noise we call sonic fatigue loading to a structure and then structural damage. So essentially, you create, based on this spectrum of loading, the spectrum for the sonic fatigue, sonic loading is created for every part in different regions, and then they are analyzed for sonic fatigue. So essentially what this is just showing schematically, you have a jet nozzle and it's creating exhaust. Usually the maximum noise occurs between 15 and 30 degrees from the center line. So all those parts which are in the vicinity of this are encountering high cycle fatigue. Can I just, excuse me, I need some water. Let me just get water.
Please go ahead.
Sorry for that. Thanks. Okay, now so as I was saying, so this is jet exhaust, and the maximum noise usually occurs in these areas, 15 to 30 degrees from the jet center line. And jet noise is a function of VR minus VJ. And sorry, this is VA, not that is aircraft speed and VJs. So aircraft speed at that time is low, and jet exhaust speed is high. So therefore, maximum sonic fatigue load just before takeoff will occur, because jet thrust is very high at that time. And this lasts only for about a minute or so, usually. So sonic fatigue loads created by jet stream, maximum overall SPL sound pressure level of gas jet mixing occurs at an angle approximately 15 to 30 degrees, which I said. OSP will depend on distance from the gas jet, angle from the jet center line, Mach number, fully expanded gas jet area, density ratio of fully expanded jet to the ambient gas. So many parameters. I won't go into the details. Here, just if somebody is interested, wanted to know what is the definition of this sound pressure level and overall sound pressure level. So I've just provided the SPL, which is sound pressure level, is 20 log PRMS, that is pressure, RMS pressure divided by PRF. PRF reference is normally 2 to the minus 5 Pascal. And so PRMS is defined by this integral. So reference is sound pressure in PA, usually chosen as the limit of hearing of 20 micropascals. Overall sound pressure level is defined by just a summation of various SPLs. Again, here logarithmically, which defines overall. So again, there's a lot of publications you will find on this. Won't be able to go into the details of that. Sonic fatigue compliance, determine the sonic spectrum, SPL versus frequency, and OSPL versus locations of the structures for various structure locations. Analyze the structure for applied OSPL overall sound pressure level with allowables based on coupon element test data. Model the sonic spectrums applied to the structure using FAM. Determine sonic response, strain distributions, and fastener loads. Perform a structural test and validate the predictions. Analyze the structure for applied sonic fatigue loads with available SN charts for joint stack. So what normally is done, you generate the sonic spectrum for a particular part at particular location. And based on that, determine the fatigue fatigue stresses, because that is related to RMS. And then you have to determine, based on that RMS level, what is my allowable RMS for a particular part, a structure. For the number of cycles, normally it will be something like 10 to the power 8 or 10 to around 10 to 100 million cycles would be usual for sonic fatigue. So there are charts which are prepared for the fatigue life. It's a low cycle fatigue. It's not easy to determine the allowables also for low cycle fatigue. So that is how the compliance is done. And also testing the component. During 787 program, we tested the whole component. I think I've shown over here. So during 787 program, the compliance was done through analysis, supported by the test evidence. And so for every analysis method, we have to demonstrate the test to verify that analysis method is appropriate. And that's the part of the certification. As I said, certification by analysis, verified by test. It's not purely by analysis. Test verifies the analysis methods, and that is how FAA accepts the certification. However, in future, suppose you are creating a similar component using the same similar processes, similar materials, then probably like Boeing would be able to certify based on the data which has been generated during 787 program, as long as the structures remain similar in design, materials, and processes. Otherwise, they would have to demonstrate again by testing the component or elements or coupons based upon the complexities of the structure and the amount of changes occurring in the structure. So this one, as you can see, this is inboard flap 787. And this was again done in Seattle. In Melbourne, we don't have this testing facility for sonic. We made it over here and it was provided for testing in Seattle. So you can see sonic test chamber. It was put in the chamber, and then depending upon the spectrum, what we had for this, we had to test for a particular overall sound pressure level, and then show using the analysis also that it simulated similar modal distribution modes of vibrations as the test indicated. There were lots of strain gauges. There were some damages also like BVIDs to demonstrate that BVID does not become detrimental due to the sonic fatigue spectrum. Trailing edge fasteners. So the demonstration had to be done for the trailing edge fasteners because in 787 design, trailing edge fasteners are very critical. And sonic fatigue test successfully demonstrated structural integrity met regulatory requirements. Okay, Now, component test.
Dr. Garg,
Yes, please. Sure.
the sonic test chamber, is it something similar to the wind tunnel test we do, or is it totally different?
No, this is what happens. This one is not a wind tunnel testing. Wind tunnel will create the flow, aerodynamic flow, while in this one, they have the loudspeakers.
Loudspeakers, okay.
Yes, loudspeaker creates a noise.
Mm-hmm. Okay.
They will generate the different frequencies and the sound level, which will create appropriate overall sound pressure level.
Okay.
So there were several speakers in this building. So you are just providing the flap attached to this. You can see some fittings over here.
Yes.
Supported through the fitting.
Right.
And so essentially, and then on I think they're mounted over here, speakers.
Okay. And the sensors are primarily strain gauges, are they?
Pardon?
The sensors on the component are primarily
strain gauges over here, just to demonstrate, because what happens, the modeling of that particular sound pressure level was done on the structure. Now, structure will create sound pressure. Basically, the sonic load is nothing but sound pressure levels, which are pressures, distributions. So pressures, they will create structural deformations, the vibrations of some modes, modal vibration. And then there will be strains generated. So that is what was noted and shown. So mode shapes were looked into. Due to this, there will be created some mode shapes, and that was studied using finite element method and try to match the mode shapes behave similarly as the analysis showed on the component. And also the strains on the skins at various places.
Right, thank you.
And third thing, the most important thing was these trailing edge fasteners. Because in our structures, our typical design of this 787 trailing edges, the trailing edge fasteners are critical. So at that time, FAA had all been concerned about the trailing edge fasteners on these structures, and we had a lot of work done to demonstrate the compliance by fatigue testing of the components, coupons, analysis for the trailing edge joints. And that is why, in fact, I keep on emphasizing everybody that joints are the most critical in the structure. Because we had a lot of experience about the joints, criticalities.
Right.
Okay, next one is a component test. Now here, so the purpose of the component test is the test articles are configuration representative of actual structure of full-scale components, verification of internal loads model, and resulting stress, strain, and deflection predictions, large-scale verification of design and analysis methodology, just to verify that you have analyzed all of the structure and have we missed out anything which may be shown up by the full structure testing. Secondary effects and redistribution of effects of loading, which are difficult to be considered from a simple analysis or coupon testing. No detrimental growth or damages, verification or repairs on large structures. So we had to test each of our components. When I'm saying each of component, basically the component initially when we are producing each design. So test article general features. Test article is a production type article. It has to follow when the test articles are created. They have to be produced under the production environment, exactly the production process, which will be used for delivering the product to the airlines. There won't be any change in the production process, what we have tested. So the same process which is going into the production of the component, so that it validates the production process. Simulate the reliable process anomalies. Another thing is just to demonstrate that any undetectable damage or detectable damages do not propagate or create any detrimental effect on the structural integrity. So production anomalies like dismounts, delaminations, they were created at the time of manufacture. Because that is a compliance requirement. We have to consider any damage which is undetectable could be during production, like delaminations or dismounts. And then incorporate the BVIDs and BIDs. BVID, barely visible impact damages, and then VIDs, damages, to validate no damage growth. That is a criteria of the structure. Install the strain gauges to measure strains and LVDT for displacements. Verifies the predicted strains and displacements. That is verifying this analysis methods. Structural repairs, verifies the repairs. So all these parameters had to be considered for the test articles. Typical test flow for static test articles. So test article fabrication, production anomalies, create BVID, instrumentation like strain gauges, LVDTs, mount test on the test rig, visible and entity inspection, load it by 60%, and then load it to the limit. Now this load 60% limit load is applied just to verify that your strain gauge is working okay, LVDT is working okay, all the systems are working okay. So just a strain verification. Then limit load, apply the limit load. Various load cases. There could be 3 cases or 4 cases critical, like one could be torsional critical, and there could be bending critical, or third one could be another load critical. So critical load cases are applied. And then I've not shown over here, then you will inspect the parts just to show that there's no permanent deformations, because that's a requirement when you are applying the limit load. There should be no permanent deformation to any of the structure like metallic fittings. So at every step, in fact, I have not incorporated over here. So at every step, there would be NDT and visual inspections for the whole of the structure. So basically inspections at every step. Then ultimate load, that is critical load cases. There could be 3 or 4 load cases which could be applied. And then after each load application, try to inspect the part. Detailed inspection, essentially, just go around, see if there's any damage, do some NDT, visible NDT inspections to determine any damage to any part, incorporate then visible damage, what is after, because certification requires, of course, as you might remember from my damage tolerance diagram, that all the undetectable damages have to sustain the ultimate load requirement. And that is what is done. Here, undetectable damages, BVIDs, delaminations, dismounts. And then once you are loaded to ultimate, so that means it has met that compliance, the first zone or category 1 damage. Then you have to create visible damages, like VIDs. So we created larger impactor damages and also machined some notches and holes. So visible and entity inspections. Sorry, this is inspection, and incorporate visible damages, and then load it to the requirement for visible damages. Residual strength requirement is the limit load. So here we are loading to only limit load, not to ultimate load. Large damages. And then repair all these visible damages. And the requirement is after repair, the structure should be able to sustain the ultimate load. And that is what its ultimate load requirement. And once loaded to ultimate, then visible and entity inspections. Now, one would ask, why don't we load it to failure? Failure, that's not a requirement for FAA. And generally, we don't try to load it to failure. There's no use. It just may satisfy, okay, it may go to 120%, 150%. But what we are trying to show by analysis, once it has shown by analysis that the strains and LVDTs are working well, then I'll show in the next slide the compliance procedure. So this is the inboard flap you can see in the test rig. It's loaded by the forming boards. These are forming boards, and through the filtry, and they're the actuator, hydraulic actuators supplying the load to various actuators. So here. Okay, now, so what do you do? This component was installed with dozens of strain gauges on the skins. Some gauges were back to back also to demonstrate the buckling. Then LVDTs to read the deflections. And the results are for certain gauge. Now, this is just some typical reading. One slide I've taken from our actually structured data, which is published, could not show any the real strain values here. We were not allowed to show any strain. So what you can see here, the test versus analysis. Prediction of skin stress agreed well with test data, verifying the analysis methods. The requirement was very stringent about it, matching the strains of the test data to the analysis within plus minus 5%, which is not easy, let me tell you. For the structure, you are analyzing larger structure, and how the skin strains behave could be quite different to your analysis than test. Right. So what happened really during the analysis and testing program? We got the test data, and test data in some locations were deviating more than the required matching of like agreement between the test and analysis by more than 5%. So then it it had to be analyzed. Structures had to be reanalyzed because our AR, authorized representative of FAA, will not accept the results of the test and analysis until we had demonstrated that the agreement within plus minus 5% between the test and analysis, because the requirement is if you can't meet that, means your analysis is not working fine. They don't have any confidence in the analysis method. And after testing, our engineers went again to modeling, tried to investigate, okay, modeling, looked into fastener details, the elements, and looking at element types, thickness changes, all those, tweaking the figures in the analysis to match the test data. So initial analysis probably would have taken, say, like 6 months, or say less than that, of course. And then after test, several months were required again to match the test data. It was not an easy task, but one has to do it to show the compliance for the certification. And this takes a lot of time. One can think, oh, we have used the FEM method and look, Nestan or Abacus, they should predict the results perfectly well. It's not so. FA doesn't accept it. And after we had demonstrated, as you can see, how well the test data are matching with the analysis, that gives a confidence in the analysis method. The type of the elements, type of modeling, perfectly matched. So, well, these are the things which you learn only in the industry. The complex procedures of certification. Next one, the displacements. Using LVTT at various locations, so the trailing edge and leading edges, because you predict the deflections using finite element methods, and then using the test. What happens when you are using a finite element? There could be differences in the analysis because the stiffness which you are representing using the finite element methods may not be exactly the same. The laminated stiffnesses could differ from one point to another point, and that will change the deflections. However, again, the requirement was within plus minus 5% for the FA requirements. And then engineers had to work in order to match the stiffnesses exactly what was the test showing and the analysis showing. And you can see the result, they're pretty good. So our engineers at the time had done a remarkable job in analyzing the sophisticated structures and matching the test data to provide a full confidence in the analysis methods, which is enormous task. Why I'm trying to, emphasize on this, when you join the industry, the compliance requirements are very strict from FA. And errors between the analysis and test is not acceptable by regulators. It has to be very good. And that is why our analysis tools have to be excellent so that they match the test data exactly. Any questions so far on this from anybody? No? Okay.
Sir, just 1 second.
Yes, sure.
Sir, in that sonic fatigue analysis, what exactly are we looking for, sir? Because analysis-wise.
What happens, sonic fatigue? Actually, I have not put any details over here because there was no time to put lots of details. I've taken away. So essentially, sonic fatigue, say, suppose we are dealing with this flaperon over here. Due to this, it creates vibrations. Now, these vibrations which are there, low pressure, high cycle vibrations, it's a fatigue loading essentially. So you have to generate using a sonic spectrum the amount of loads which are being created. Fatigue load is essentially converted to the fatigue load, the pressure distribution in various zones. And that fatigue load is compared for the fatigue endurance limit using the stress fatigue diagram, stress cycle diagram. I could provide some notes in the question answers next week to discuss a few more detail. But there's a lot of work in this sonic fatigue compliance. But imagine a situation, it's like a mechanical fatigue. We have the loads, so you generate from this sonic fatigue the loads, you convert these pressure cycles, or when we are calling sonic OSPL. So in terms of the loads, it can convert it pressure distribution or this stress. And number of cycles for which you have to show the compliance. And then compare with the SN chart if you have for that part, for that high cycle fatigue. So essentially, it's a fatigue problem. High
So
cycle.
basically, are these loads obtained from analysis?
They are based on basically the test data. The spectrums are generated by test and validated by analysis. Analysis verified by test. So Boeing would have generated a lot of sonic fatigue spectrums by analysis, which
Dr.
would have
Garg,
come from the, yes.
Yeah, just to extend on that,
Yeah.
I also perhaps it's so that when we talk about sonic fatigue, we are essentially perhaps talking about very high frequency signal also compared to mechanical fatigue. Mechanical fatigue, I think we will be talking about few hertz or tens of hertz, whereas when you talk about sonic fatigue, we are getting into kilohertz and tens of kilohertz perhaps.
Yeah, generally the spectrum lies between 100 to around 1000 hertz. Yes, you are right. So they are very high cycle, high frequency.
And the effect also will be different from mechanical fatigue.
It is different. So it's a complex analysis. It's not simple, in fact. So we had to demonstrate by test. However, Boeing has historically got a lot of data for demonstrating the compliance using sonic fatigue on metallic aircraft. Those methods have been developed over a long period of time, and composites also. In fact, composites, essentially, we were the ones who had to determine the compliance for the fatigue of this sonic fatigue of all these components using the analysis and test.
Professor Garg, I have continuation question. This it will be hot gases basically along with the sonic frequencies. So whether this high temperature will also affect the fatigue behavior, is it considered? Because when we do speaker test, it will be only the pressure load, but not the temperature load.
Well, this region is not that high temperatures, in fact.
Okay.
This is away from that zone where high temperatures. So these structures are not that at a higher temperature. They are within of the limits of design. Less than 70 degrees centigrade would be the temperature, because our design condition for this is around 160 or 70 degrees centigrade maximum. So it won't. They are not in very high temperature zone. All this high temperature zone is over here. So these parts don't lie in that zone.
Thank you.
Okay.
Sir, is there any failure observed during sonic fatigue?
No, there was no failure.
Okay.
So
because the load
Thank
will
you,
be
sir.
very low.
So depending upon the loads, actually, whether it's 160 dB or 155 dB, 165 dB. So we had to demonstrate for all the dB requirements. So these tests were done considering the overall pressure, sonic pressure levels.
Okay, thank you. Thank you.
Yeah. Well, I said I can send some reports, actually, NASA references on sonic fatigue. If somebody is interested, high cycle fatigue. Okay. So I was discussing this, and essentially what I said, that analysis confidently showed that the test matched the analysis data. So confidence. Another thing which I said, okay, in order to show the visible damage, a large notch was created in every flap. Of course, the large notch was done. This is only showing a part of the inboard flap showing upper skin. As you can see, a large notch right up to middle spar from trailing edge. So large notch IV flap upper skin for demonstrating damage tolerance compliance. No damage growth noted after test to design limit. So it was tested to limit load carrying capability and no damage growth. Inboard flap and other empty components. Fully skilled straight test met the following objectives. Test strength and displacement agreed with the predictions and thus validated the analysis method for each of the components. No damage growth observations observed from undetectable detectable damages. Test successfully demonstrated the ultimate and design loads capabilities per regulatory requirements. So they're satisfactory. They satisfied all the compliance requirements. Okay, fatigue test. No detrimental. I think this may require a bit of a discussion, fatigue, and maybe I might spend about half an hour next week to finish off this fatigue test. And I can stop here now today and invite the questions if somebody has any question. Any questions?
Dr. Garg.
Yeah.
Yeah, the fantastic series of lectures on all these, very, very valuable and not easily available elsewhere. So thanks for this. I have a general question. So all these aspects covered so far, though are referring to the MTE, that is movable trailing edge, I presume the philosophy is more or less the same for all the other structural components, composite components as well, of maybe with a little bit of variation here and there. Is that so?
Well, it's a compliance philosophy is same. And I picked up this example because I worked on this MTE structure, but certification philosophy with wing or empennage, fuselage is similar. Right. Same requirement. Essentially, the requirement comes from, main requirement is that damage tolerance. And this is what I have covered over here. Right. So this diagram, which is there, let me just go back to. Essentially, we have to cover this diagram. That, and this is whether whatever structure you have to demonstrate the structure capability with undetectable, detectable, and immediately obvious damages. Right. This is what I've tried to cover in this lecture series, that certification philosophy is to show the safety of the structure, and safety of the structure is from the damage tolerance point of view.
Sure. Yes. Okay. Thank you. Thank you.
In fact, there's another article which I had sent, which was done by our colleague in Seattle quite some time back. Wrote the certification philosophy for 777 empennage structures, and that was similar to what is included in my lecture series. So almost 25 years back, 777, almost more than 25 years back, it was certified. And that presentation paper by Alpha Set, which I had sent, which is similar to this one. So same philosophy, there's no change in the philosophy. The compliance is to be demonstrated for FAR requirements. Any other question? One of the action on me basically is put some more details for sonic fatigue, and I'll send you some literature on that noise, cabin noise. Anything else? Any other questions?
One quick question, Dr. Garg again.
Sure.
We were talking about visual inspection and NDT inspection. I work in NDT here actually.
Yes.
So I was just wondering whether we have little bit more information as to which are of high importance or high utility there. Is it ultrasound, contact method, or is there eddy current, or any idea on this?
Well, generally on the composites structures, we don't use any eddy currents. It's mainly ultrasonic.
Ultrasonic testing, yes.
Yeah. Ultrasonic, various different type of ultrasonic inspections are done to detect the damages. And these methods have the limitation that you can't detect the damages below a certain limit, like a quarter-inch hole or quarter-inch delamination, not the hole, but delamination disc bonds. And that is why usually, as an undetectable damage, the disc bonds are considered like a half-inch by half-inch defect, which will remain undetectable as a disc bond or delaminations inside the laminate.
Right. Okay. Thank you.
You're welcome. Any other questions? Okay, if there are no questions, then good night or good evening for you people.
Yeah, thank you very much, Dr.
See you next week.
So we'll wind up this course on Monday, I guess, and then
Monday should
resume the course on joints the same day.
Yeah, we can start that.
Yeah, sure.
And I'll send the lecture note.
Sure. Thank you very much. And for the sake of the audience, the files that Dr. Garg mentioned, they're all uploaded to the Teams. So any of you are interested can keep downloading them as and when you require. And as he keeps sending new ones, I'll be uploading those as well to the team. Thank you.
Maybe what happens, question answer every day updated one. You should delete the previous one so that people just have the latest version.
Sure. Yeah.
Okay. Thanks. And good night.
Good night. Have a great weekend.
Thank you, sir. Bye.
Thank you, sir.